Good morning, everyone. Hi. How's everybody doing today? Good, good. I'm glad to see you all. I missed the last one and I heard it was very awesome to see all the music stuff, so we're hoping for another awesome talk this morning. This is our 5th lecture in our Saturday Physics for Everyone series this fall. Our 6th and final lecture will be on December 7th. Yes, December 7th. So if you'd like to sign up for that one at all, you're free to add your name to our email list using the sign-up sheet up front or scan one of our QR codes, and you can do it on electronic version. So if you haven't met me before, my name is Irene Lyra Ansager, and I'm the coordinator of undergraduate recruiting, research, and placement here in the physics department, which means I get to talk to prospective physics students, and I have seen some in the crowd this morning. And for our current students, I help them find research opportunities and think about what you're going to do after graduation. So if there's any questions regarding those things from anyone in the audience, I'm here to answer those. And our lecture series, Saturday Physics for Everyone, is developed to introduce our community to some of the awesome things we're doing in the department, and for our high school students and other people interested in the physics major, get you an idea of what you might be studying in some of these different topic areas. So, without further ado, I think I'll introduce our speaker for today, Professor Chen-Yu Liu. And she is a full professor in the physics department and the nuclear physics laboratory here at the University of Illinois, Urbana-Champaign. Dr. Liu completed her doctoral research experiment in experimental nuclear physics at Princeton University, followed by a postdoctoral fellowship at the Los Alamos Neutron Science Center. She is also an alum of the National Taiwan University. She previously has taught at Indiana University from 2005 to 2022, when she was then recruited to come here to be with us here at the University of Illinois, Urbana-Champaign. Professor Liu's research focuses on symmetry tests and fundamental neutron physics to understand matter creation and nucleosynthesis in the early universe. She specializes in experimental tools using ultra-cold neutrons. And in her dissertation work, she solved the critical issue of excessive loss of ultra-cold neutrons and made the world's first working solid deuterium, which is heavy hydrogen, source for ultra-cold neutron production. This breakthrough has prompted several investments of ultra-cold neutron facilities around the world. She has also studied magnetic excitations in cryogenic oxygen solids for ultra-cold neutron production. And between 2011 and 2016, she led the ultra-cold neutron tau experiment, which now holds the record for the most precise measurement of the neutron lifetime. In 2018, Professor Liu won a National Science Foundation major research instrumentation grant to construct a room temperature apparatus for improving the measurement of neutron electric dipole moment. So if you could please all join me in welcoming Professor Liu.
Can you hear me? Okay, great. Well, thank you, Irene, for the introduction. So when I was asked to give this public talk, I was actually struggling, like whether to introduce the audience my research or really try to serve the mission of the Saturday Physics Morning Talk to more present information more accessible to general publics, in particular at the level of high school students. So my family moved here 2 years ago to Urbana, and my daughter just started at uni high. So I'm thinking that, what can I present so that she can benefit from this lecture? After all, she already heard a lot of the ultra-cold neutron discussions over the dining room table. So I decided to do something different. That's not really the main topic of my research, but I think that could be of interest to a lot of people. But anyways, you probably don't know that every state in the United States has an Office of Weights and Measures. Those offices are there to ensure practice for fair trade. So like all scales in grocery stores, okay, the pumps at the gas station, they all have to be properly calibrated to make sure that consumers pay exactly what they purchase. So here you can actually go to the website to find out the Office of Weights and Measures. They are under the Illinois Department of Agriculture. And everything, all the calibration devices have calibration traceable back to the NIST, National Institute of Standard and Technology. They run a world-class physical measurement laboratory to perform necessary calibration on all the measurement devices. There are many different physical properties that we measure every day, right, on a daily basis, from the laboratory to on the street, and then to why you have to go to a grocery store to purchase. So then there are also many different units. Everything can be reduced to the 7 base quantities, each with their units. So we have time, that's measured in second, length, measured in meter, mass, measured in kilogram, electric current, measured in amperage, thermal temperature, measured in Kelvin, amount of substance measured in mole, so those start getting more actually scientific. Luminosity intensity measured in candela. Okay, so this is a particular system, because you did not see pound here. Okay, we're using the international system of units. This is the SI unit. It's a matrix-based unit because that seems to be the simplest one for particularly scientific application. I will not have enough time today to cover everything, so I'll just focus on this particular quantity of the mass measurement. Okay, let's start with what we are familiar with, 1 pound. So this 1 pound has its original definition coming from the French system, our Dupois pound, that equals to 16 our Dupois ounces, but then not what is ounces. Then they also, this pound also equal to about exactly 7,000 grams. And then grams is actually a measure of weight that's based on the mass of a single ideal seed of a cereal. So what is ideal seed of cereal, right? I mean, obviously depends on what kernels of seed you are talking about. For example, this carob seed, okay, is actually the mass measurement of 1 carat. That's people use to measure the amount of a diamond. This equal to exactly the weight of 4 wheat grains or 3 barley corns. Okay, and there are so many different corns, so many different products. So it's really getting confusing. Also, we can never really define what's a condition of an ideal seed, right? Depending on the weather, the production. Very soon, people actually come up with this standard. So this is a 1 pound standard. It's just a piece of mass here. It's made of brass. Now it's stored in a museum in France that you can go check. Similarly, we also have in the matrix system, we have this international prototype of kilogram, or IPK, Lagrange K. So this is, again, the base unit of mass measurement, but now in matrix system, okay? So the whole idea of defining matrix was, the original idea was proposed by John Wilkins, saying that the volume about 1 meter cube filled with rainwater, the amount of weight should be equal to 1 kilogram. So that was the early definition. However, this proposal was never adopted. Okay, so it's very nearly equal to 1,000 cubic centimeter of water. And then between pound and a kilogram, it has a relationship. So a pound is about half of a kilogram. Okay, and then similarly, there's a mass here. It's smaller because this mass is made of platinum iridium alloy that's more dense. That's about 90% platinum and 10% iridium, because For platinum, you can have extreme resistance to oxidization, and you can see that it's really properly protected under many layers of bell jar to ensure that, to evacuate the atmosphere so that to prevent the surface from being eroded away by forming oxide with the atmosphere. So you have to protect the standard. Once you define, say, this particular object is my 1 kilogram, you don't want this 1 kilogram to change. Okay, you want it to remain there at all time and stay the same mass there. So there's a lot of precaution put in to protect the stability, to ensure the stability of this mass standard. It was kept in a vault in International Bureau of Weights and Measure that's in Paris. And when this was first made, there were 6 identical copies made, and then they were all stored in the same vault at the International Bureau. And then additional weights were also made to be distributed across the world to different countries. Okay? So then when you have trade between countries, and we make sure that we are referencing to the same kilogram standard. However, the problem is that those physical mass, they were first produced before 1900, and then over time, then the mass actually changed with time. So they brought back about 40 years after to Paris and remeasure again, find out that the weight of all those identical copies now are all different. Then they can vary by as large as 50 microgram. Okay, it's a really small change. Okay, it's a part per billion type of change, but still you can measure microgram with a sensitive scale. Okay. And then as time goes on, this variation just diverged. So therefore, it's really not ideal to use a physical object to define what 1 kilogram is. So realizing that, then physicists think that maybe we can try to improve this practice by using something different. Okay, the International Task Force on the Committee on Data for Science and Technology is called CODATA. They have a task group, and they propose to redefine the kilogram using a fundamental physics constant called Planck's constant, H. Okay, so Planck constant, where's the Planck's constant comes from? Planck constant actually is related to the energy of a photon emitted. Okay, or light anywhere. It could be coming from the sun, could be coming from the excitation of excited molecules, but then the photon comes out, the light comes out, carries energy. And then this energy is related to the oscillation frequency, and then with a constant here, h. So this is where the Planck constant is. So this is actually fundamentally quantum. Okay, and then this can be measured using all different type of atom in all different laboratories around the world. Okay, but now the problem is that how does one actually relate a kilogram to a Planck constant? Something that's macroscopic to something that's very small, acting on the quantum scale. All right, so now the trick is to use this Keeble balance at the National Institute of Standard Technology. So this is a very complicated device that you have to put in the vacuum chamber to evacuate all the air, and then there's sensitive calibration devices inside there. And then it's actually a balance, okay, the world's most precise balance. And then this balance, before 2019, this is a device used to measure Planck's constant. I will explain to you how this actually works. And then at 2019, CODATA group get together and decide, okay, now we measure this Planck constant to as precise as we could achieve at that time. So now we're going to just say Planck constant equal to this number that was measured. Okay. Now, once you said that, after 2019, now this device is used to compare the force on the 1 kilogram to the force that can be measured using magnetic field, and then referencing that to the Planck constant. Right. Now, how this works is that here, this is your Keeble balance. It has 2 arms here, so it's a balance. And then on one side, I have my 1 kilogram mass sitting on this measurement plate here. But so gravity obviously is going to pull this mass down. So to keep the mass balanced, and then you need a repulsive force to keep the mass there. Yes?
Won't the weight change
the weight. Oh yes, the Earth's gravitational constant will change. Exactly. Yes.
So where do they keep it at a constant elevation?
Oh, they have to measure the local gravitational field every time they perform this measurement. Okay, so the gravitational force here is mg. It's the mass multiplied by the Earth's gravitational acceleration constant here. So that's a downward force now get balanced out by a magnetic force. So I can put current into this coil, and then this coil is going to now magnetize, produce a magnetic field that opposing this another static magnetic field that I already put around the apparatus. So now I can create some magnetic levitating force on this whole assembly. As long as these two forces cancel each other, okay, now the weight is balanced. Okay, so now I can relate my weight, which is the gravitational pull on this mass, to magnetic force. Okay, now I just need to have another way for me to figure out exactly how big that magnetic force is. So in this, to do that, then I will operate this in a constant velocity mode. Means I will pull on this arm so that the whole balance vibrate back and forth at a constant velocity. Okay. Now this motor, I can measure this velocity very precisely, and then as a consequence is that now I have a coil that's moving, as a conductor moving in a magnetic field. It's going to induce voltage, okay, due to Faraday's law. And then this voltage now I can connect to my oscilloscope or a digital meter to measure that voltage very precisely. All right, so you can see that this two equation, I can now measure mg, okay, and multiply by the velocity now equals to the current that apply and multiply by the voltage that's induced in the constant velocity mode. So in one side, this actually give me physics quantity is a power. It's a mechanical power, okay, related to the object moving at a constant speed. Now on the right-hand side of the equation, now there's a current multiplied by voltage. So if you have some electrical, electricity course, you realize that this is actually the measure of the power, electric power. So that's why that this balance is also called the watt balance. All right. Now, this is what we're trying to measure, mgv here, now equal to IV. So I is the current, okay, and V is the voltage. So how do I do this measurement? Now, the best way to measure voltage, most precise way to measure voltage is to use something called the Josephson junction. It's a superconducting device, okay? So I have a superconductor here, and then I induce some kind of a weak coupling in between, break the coupling in between. Then this has become a sensitive device. When I shine some radiation with no frequency throughout this, it's going to excite electron in such a way that there will be voltage induced across this junction. So this is called the AC Josephson voltage. And then you can see that this voltage is quantized. So therefore, this phenomena is truly quantum. And the level difference is proportional, is equal to H, it's the Planck constant, frequency of the RF radiation that I shine onto it, and divide by twice of the charge of the electron. So this is actually a really precise measurement. Now I can measure this voltage using this Josephson junction. I can actually, there's a device, each one of this is very small, tiny voltage, but I can string array hundreds of Josephson junctions together to get to a voltage that's comparable to what's induced on the coil, okay? Now what about the measuring current? Current can also be related to voltage measurement, right? So you just take Ohm's law voltage divided by the resistance. And then in this case, now the voltage is quantized here, okay? And then now the resistance, okay, is actually measured using, again, another quantum effect called the fractional quantum Hall effect. I won't get into detail into that. But all you can see is that this R is the fractional quantum Hall number here, and then also multiplied by the Planck constant divided by the charge square. Okay, in the end, you can formulate all this together. So now mass is equal to P is the fractional quantum number which I can measure. N squared also I can measure. Frequency is what I apply to the Josephson junction. And then divide by G is the Earth's gravitational field. So that's what you ask. We have to do independent measurement of this gravitational field. Velocity we can also measure, and then Planck constant.
Why for the resistance we use fractional common for rather than integer common?
Well, I think that's actually more precise in a way. I don't really know much detail about this, so maybe I can get back to you. Yes.
But doesn't the Earth's center of gravity change from day to day?
Yeah, of course. It could change from day to day, right? Depending on the water level, depending on where the moon is, right? So every time you do this measurement, you have to actually also in parallel measuring the Earth's gravitational acceleration at the time of measurement. Yes.
Back on the previous one where you were measuring something about, like, you were talking about Planck's constant,
Mm-hmm.
you put up the equation, or like E equals NHF, where NH is Planck's constant, and F is the frequency of the light.
Mm-hmm.
What's N?
N is how many quantons. So those are, if you can see that how many levels are quantized, and you can just count those number of quantons. Yeah. Any other questions? Right, so here you go. Now I can actually relate my 1 kilogram to everything that's either could be measured or is something that's fundamental. Since H now is defined, is fixed, so now I only have to perform the measurement of the frequency measurement, velocity measurement, and the gravitational field measurement, then I can get to the mass. So in this case, now to get to the mass measurement, okay, on my SI table, I only have to, actually, now go back here. Yeah, so now the mass is related to the Planck constant. I also want to actually illustrate this idea of redefining the kilogram using the example of redefining the meter. So kilogram right next to that is the 1 meter. So 1 meter, to define 1 meter, you use 2 fundamental constants here. Okay, one is the definition of the speed of light, and the other related to the definition of the second here. Okay. So the meter has been redefined actually much earlier, okay, in 1983. So it's been redefined as the length of the path traveled by light in vacuum over 1 second. Okay, divided by this number. Okay. And the second, how do we define 1 second? It's defined by using CCM atoms. We can measure the light coming out from CCM atom, which absorb and emit microwave radiation with specific frequency. We can measure this frequency very, very precisely, okay? And an atomic clock, now 1 second is defined by this oscillation of the microwave for about 9 billion times, okay? Once you have a CCM atom, I count this many times, that's giving me 1 second, and I take that 1 second, and I see how far the light travel in the vacuum, divide by this number, then that's my definition of 1 meter. Yes?
Do all atomic clocks use cesium atoms?
I don't think all of them. CCM is relatively easy to use. Okay, and then with laser wavelengths readily available. But I don't think it's the most precise one, but they are very easy to use. All right. So just like the IPK, the meter also has an actual object. That's the meter standard. So this was created with 1 meter using platinum alloy, and then several copies were made. In the US, we actually got national prototype number 27, that's right now at NIST. So to monitor this length, you found out that the length of this 1 meter actually depends on the temperature, okay? So because it's thermal contraction. So you have the control, you have to know the temperature coefficient. You also need to actually make sure, again, this doesn't get oxidized and then lose mass. So it has the same issue as defining kilogram based on mass. So now instead of using this prototype, now we can use this prototype to measure, say, now we know start with this 1 meter, and then we use that to reference and measure the speed of light traveling in vacuum. Okay, So it's how far the light travel over some certain time, right? And then since this is the actual measurement, you have some uncertainty associated with that. Okay. Then people decided, okay, now since meter doesn't really have to be set to a specific value, so we'll set the meter in such a way that speed of light is exact with no uncertainty. Okay. Now, once I have a speed of light, I can come back, now just use the speed of light to see how far the light can travel in vacuum over 1 second and divide by this number to redefine the meter. Okay. So that's the trick physicists are playing. And now we have the length of the meter defined, not using a physical bar, but now referencing to the concept of speed of light. So it's a similar idea. Now the kilogram no longer refers to a prototype object. Okay, now it's actually referencing to a concept. It's the physical constant of the Planck's constant. And then this constant, as we believe in physics, shouldn't change. Should be independent of when you do the measurement, where you do the measurement. It should be the same, okay, everywhere for a really long time. Right, the next related concept is the mole, okay? So the mole is the unit of measurement that presents specific number of atoms, ions, or molecules, okay? So you probably encountered this concept in chemistry. In chemistry, 1 mole of carbon contains this number of carbon-12 atoms, and it weighs exactly 12 grams. But now the question is that how do we know it's exactly this number of atoms, right? After all, you cannot put this under a microscope and then count the atom 1 by 1. Even if you could, you can never really count to this large number, okay? But 1 mole is a convenient unit to relate any substance of physical weight in grams to bridge the gap between atomic mass and the mass that can be physically measured. All right. So then now let's actually get back to the question about how do we know 1 mole really contains this number of atoms. So this number is called the Avogadro's number, okay? And then how do we actually measure this Avogadro number without having to count all the individual atoms? So this, again, physicists came to contribute here. So this is an image, a microscope of pollen grain actually moving around in water. So this water is at room temperature. This was discovered in the 19th century by Robert Brown, and that's why it's called the Brownian motion. Okay? So at that time, people didn't actually know the concept of atoms. So now the question is that what powered the motion of those pollen grains? Until about a century later, Albert Einstein actually was very interested in this topic. So then he came up with this hypothesis. This polar grain was moving around because the particular grain is constantly bumped by water molecules. Okay, the water molecules are colliding, and there are so many of them, so that they exert instantaneous some net force that causes this object to move and then wander around the liquid. Okay, so this is called the Brownian motion, and then you can do something quantitative. Say you start with the atom here, a pollen here, and over time it's going to wander around in the substance, and then no matter independent of the actual path it takes, what you can do is that you can try to measure the displacement. How far is this pollen particle move away from its original position? Okay, so you can do some math here. Turns out that this is called the distance. The average distance over time is the diffusion constant. Now this is proportional to the temperature of the water, and then R is the ideal gas constant. Again, that can be measured in a lot of chemistry experiment. Divided by this NA is the Avogadro number. And then over 1 over 4 pi R to the cube. So this is the size of the pollen atom here, and then the viscosity of the medium, of the water. So Jim Perrine at that time, and he actually proposed, he realized that, oh, actually this is exciting. And if I can actually get the pollen size to be very precisely, so he actually used centrifuge to select a specific grain size of pollen grains to make sure they are the same radius, and then he can examine this behavior under his microscope. By doing that, he got the Avogadro number equal to 6.8 times 10 to the 23. Okay? And this is actually not too bad. The best known value now we know nowadays is this number. It's pretty close. So nowadays, we no longer use carbon-16, 12 grams of carbon-16 to define the number of molecules. Okay. Instead, we use another object was also introduced. This is a perfect sphere. Okay. People in Europe spend $1 million to polish this sphere. Okay. It's a sphere of silicon-28 isotope. Okay. And it's polished, so as perfect sphere, and then the volume is determined by measuring the radius. So volume is 4 pi r to the cube. Sorry, I made a mistake here. And then if you know it's silicon-28, and then we know the lattice structure of silicon-28 very well. We know it's the unit cell volume. So then you divide the microscopic size of the sphere to the unit cell of the silicon-28. Now there's another way to figure out the exact number of atoms in the sphere. Okay, so now by doing that, now we have Avogadro constant. And then we set this Avogadro constant to this particular number, and that defines per mole. And then when seeing that picture, actually remind me of the artwork by M.C. Escher here, also perfect sphere. All right, so I have actually 10 more minutes, so I'm going to go through some. So now knowing this, I would like to start to venture into something more related to my own research. Okay, so my research is on study the fundamental building blocks of nature. Okay, so they are not Legos, we know. So ordinary matters, when you put it under the microscope, you'll find out molecular structure. Okay, in the molecules, you find out they are also made up by individual atoms. When you further zoom into atoms, and then you will see electrons, you will see protons and neutrons. And then when you further zoom in, you see either more exotic particles like quarks and gluons. So we think that the quarks and gluons, our electrons, are really the fundamental building block. They cannot be further divided into further substructure. So now so atom, now we understand the atomic model, just like a solar system here, how you have positively charged atomic nuclei surrounded by negative charged electron here. Now, my goal is to weigh individual atom, okay, for example, this carbon-12. How do I do that? I cannot just isolate a single atom, put it on the scale, and then measure it, right? So how do actually physicists do that? All right, in chemistry, you can say, oh, maybe we know how to do that in chemistry. You start with measuring some grain of chemicals, and then you look up the molecular weight table. You divide that, and you can figure out how many moles there. Now, if I know the number of moles here, now I can divide by the Avogadro number, okay? Then I can actually get to the atomic mass that way. But however, to get to here, you first have to know what's the exact molecular weight, which is the weight of 1 mole of molecules, or 1 mole of an atom, okay? So to do that, we really have to isolate individual particle. So let's start with the electron. How do we actually measure electron mass? This was actually first measured by J.J. Thomson. So J.J. Thomson was running this device that's a vacuum tube here. It's a cathode ray vacuum tube. And then you can connect high voltage through cathode and anode, and then generate some cathode ray, okay, unknown particle coming out here. And this cathode ray can travel through the vacuum unimpeded, and then hitting the front, and this surface is coated with some phosphorus material, and you can see the scintillation. In fact, that's how the old TV monitors work, the cathode ray tube, okay? And now we find out that, okay, if I want to illuminate different part of the screen, I can do a trick. It's that I can actually apply a magnetic field here, okay? Now by turning on and off the current of this magnetic field, and I can steer the beam to different direction, okay? Now by doing that, I mean the mass here, okay, mg, okay, so the force exerted by the electric field and also magnetic field here, which I can calculate, is going to cause the deflection of a massive particle. So therefore, then I can measure the mass to charge ratio using this experiment. I say, still I want to get to the mass. So if I can also measure the charge, then I can get the mass of the electron. So then you need another experiment. Okay, so this particular type of technique, a charged particle can deflect in the magnetic field, is a very useful tool that physicists actually exploit all the time. For example, this cloud chamber, you have different charged particles zooming by, or either charged or non-charged, depending on whether they are spiraling or not spiraling. And then we can actually use the radius and frequency to tell different type of particle, to tell the charge to mass ratio. And then knowing the charge, and then different particle has different mass, so we can actually use this as a way to distinguish different particle that has different mass. So to measure the charge of the particle, okay, of the electron, the Millikan actually devised this very clever experiment. So you're just using drops, oils, dropping oils, making a stream of oils, droplets in a vacuum in a chamber here. And then he has a microscope set up to see the individual droplet. So if nothing happened here, the droplet is just going to actually drop under Earth's gravity. Okay. But now he applied additional electric field here. Again, using this balance idea, to use the electric force to balance out the gravitational downpour. Okay, so that it can actually make a oil droplet remain static in the view of the microscope for enough time that he can actually observe the size of the droplet that way. So now you find out that okay, he can do statistics. He can write down all the different mass of the objects of the droplets here. And then the force that need exactly to balance it has to be equal to the charge that carried by this droplet multiplied by the applied electric field. By using that, and then there are many different droplets, right? So in the end, you find out that if charge is quantized, then the common denominator then will give you the size of the charge that way. So by doing that, you can measure the charge of electron to be 1.6 times 10 to the minus 19 coulomb. All right. So nowadays, we no longer do oil drop experiment. They are actually improved experiment by putting a single electron in something called a penning trap. So the penning trap is a combination of the magnetic field and the electric field. So magnetic field is uniform applied across throughout this apparatus. So what happened for the charged particle for the electron is it's going to keep on spiraling inside this magnetic field. So it confines this electron radially. But then from the top to bottom, the electron also get kicked back into the trap by seeing this quadrupole electric field. Okay. So now this electron is confined inside this very small, tiny volume, and then this electron is doing those pretty motions, the sequential motion with axial up and down oscillation, and also forming closed cycle. This is called the magnetron motion. And physicists can actually now connecting sensitivity detectors to measure the induced current due to the motion of a single charge. And in this way, you can also measure the force and the charge to mass ratio very precisely. The same way was also applied to measure the mass of the proton. Okay, so now we have proton also put it into this penning trap here. And now the penning trap can trap different species of atom. It can trap proton. It can also trap carbon-12. So that's where we started. And then you can actually compare the mass reference to the carbon-12 that was defined, that was used to define 1 mole. Nowadays, the proton mass can be measured also to this type of precision. All right. Okay.
You're just about to answer it.
Oh, neutrons.
How do you measure a neutron?
Exactly. How do you measure the mass of neutron? So neutron, we cannot apply this trick, right? It doesn't have any charge, so we cannot really trap it. Okay, so how do we actually do that? Now the trick, we have to rely on the nuclear capture reaction. So when you have one neutron, it will want to bond together with one proton to form a bound state called deuteron. Okay, and then what we can do is that we can put this deuteron in an ion trap and measure the mass very, very precisely. Now we can also measure the mass of the proton and then do it very, very precisely. Now the difference of these two could be the mass of the neutron, right? But modulo, there's something else here. There's a binding energy, okay? So it turns out that the mass of the proton and neutron add together is slightly heavier than the mass of the deuteron, okay? Because now the two particles start from the zero energy state. When they bound together, they go into energy well, okay? So there's an energy emitted in this process. The energy is emitted in the form of gamma, okay? Now we can calculate the energy emitted here, okay, by using the crystal diffraction. So it's a gamma ray coming out using silicon. Now we can actually measure the wavelengths of the photon coming very precisely, and then relate the wavelengths of the photon to the energy of photon. Okay. So now by knowing that, I can now just take the mass of the deuteron, okay, add the energy of the gamma to come back to the original state of the neutron, rest mass of neutron and rest mass of proton. Now subtracting what I can measure the rest mass of the proton, now I can get the mass rest of the neutron. It's less direct, but however, that's a very precise way to get to that. So neutron is actually what my research field is about. You can extract neutrons out of atomic nuclei, but they are very unstable. They actually, because just like I said, the neutron actually is slightly heavier than proton. So therefore, the neutron is unstable. It would like to decay into a ground state by releasing some energy. Now the energy is carried away by electron and the neutrino. Okay, we already know how to measure the mass of the electron. But now we can ask, okay, what's this neutrino? Okay, how heavy it is. So I have another experiment that we are starting here together with collaborators at UW and MIT. We're trying to measure the mass of neutrino by looking at the neutron beta decay in the system of tritium. In tritium is a hydrogen isotope. It has two neutrons and one proton. One of the neutrons will turn into a proton, and therefore emitting a neutrino and an electron here. Neutrino, you probably heard of those. Those are called ghost particles. Okay? They hardly interact with any material. They just zip through you, and then you hardly feel its presence. But instead, we can actually measure the electron very, very precisely. Okay? So what we do is that we'll measure the energy of the electron coming out, which should carry the difference of the initial and the final state of the tritium to the helium-3 nuclei. And then we'll see how does the energy distribution look like. Turns out that there's a theory predicting this distribution. If the neutrino doesn't have any mass, it's a continuous distribution here, okay, near the highest energy of the electron. But if the neutrino does have mass, then some of the energy needs to be used to create neutrino, right? To give it mc squared, the rest mass of a neutrino. So that's the idea. By measuring the distribution, the energy tail of the electron very, very precisely, and then see how far it deviates away from the zero mass scenario, and then we can get to the neutrino mass. So this is the kinematic way to measure a neutrino. Again, indirect, but that's the best way we have. So in order to perform this experiment, the Katrine experiment it happened in Germany, and it's still taking data now. So that's the best measurement. You get a tritium source here, and then you cool this tritium source down, and then tritium beta decay, you collect the electron in the end, passing these electrons through a spectrometer. The spectrometer, the larger the spectrometer, the more precise you can determine the energy of electron, and the electron finally get collected onto the detector. You can see that the size of this spectrometer is so huge that they actually have trouble. Once this spectrometer vacuum chamber was made, it just barely fits through the street to take from the loading dock into the experiment. All right, so for the particular experiment I'm working on, we're trying to improve this neutrino mass measurement by, again, using the same technique, by collecting the electron that's emitted and in a magnetic field. Right? So the charged particle will spiral in a magnetic field. Okay? And I can calculate this spiraling frequency. It's called the cyclotron frequency. And then this cyclotron frequency actually is proportional to, again, charge to mass ratio, which I already measured before, and also the amount of magnetic field, the magnitude of magnetic field I apply. okay? And in this case, the frequency seems to be the same, independent of the energy of the electron. Turns out that those electrons are slightly relativistic, so the time is dilated. Therefore, it's going to change the time base to cause the frequency to be different, okay, depend on the energy of the emitted electron. So in that way, I can just listen to the electron coming out and listen to the frequency increase, the chirping, and then I can use that to determine the energy of the electron that way. And we're hoping that by doing this, we can improve the neutrino mass measurement to actually know a fraction of the electron volt. All right, so I have maybe a few more minutes left. I want to also talk about photon, okay? Photon is another fundamental particle, and then it has this wave property, right? Because we know we shine a light from a flashlight, and you can have those kind of diffraction and also interference pattern. And then all this phenomena can be characterized by the wavelength number. But then you can also have the light interacting with material. That's how our solar panel works, right? The sun shines light, and then the light knock out the individual electron, and then this electron can be conducted to generate electricity. So in this case, the photon actually behaves just like particle. It carries momentum, it also carries energy. And we can relate to the ratio of the energy to the momentum that equals to the speed of light, okay, which we, again, already measured. And then we also learned from the special relativity, okay, so what does special relativity tell us? That the law of physics must have the same form in all inertial frames of reference, okay, independent of the velocity of the observer, okay? So that's one thing that we know. And then the speed of light, however, through vacuum, we find out that it's actually constant, independent of the reference frame. Whether you are just standing on the ground or you are moving together with your device, the speed of light is the same, no matter how fast you're moving. That's an important consequence of the special relativity. So light travels at the speed of light in all reference frame. And then from the special relativity, we have this equation E equal to mc squared. But now if you have momentum, you have to add to that, okay? So this is what we know from Einstein, yes?
If you don't mind, I'm a physicist. I had high energy physics, nuclear engineering, and now all my life I ask the question for professors, how in the world can it be that light has the same speed for different systems of reference?
Yeah.
And after a life of work, I found that the fundamental experiment for light is missing, namely not only the diffraction fringes, but how a light spreads at large distances, as waves
Yeah.
or not as waves. And I found in 10 years of experimenting the proof that light does not spread as the waves do at large distance. And I found that a new structure of light without the Einstein thing that light has the same speed in different system of reference.
Okay. So you come up with some alternative theory
Yes,
to the special relativity.
But what I'm saying is we have to be open to a new big change, both for the experimental facts for light and for gravity. I have the proof that an experiment for gravity, the fundamental experiment for gravity is missing. So that changes both G as acceleration value, and for light is it brings. So I'm not trying to hit your explanation, but just to say that we have to be open for a new big change, which I show in 3 papers published, that light has a different structure and the gravity is the external effect from dark matter coming towards a body, or
Okay.
when coming towards two bodies, they...
Well, if you don't mind, we can talk later and let me finish my presentation.
Thank you.
Okay, thank you.
Just to say that we have to be open.
Yes, yes, okay. So physics, we have models, right? And then we try to test model many, many times until that everybody believe that that's really the truth, and then we elevate it to laws. But however, there's always the possibility that the law might not be accurate, will be modified later. So in science, that's a typical practice. All right, so now in the framework of Einstein's special relativity, right? So you have the energy here related to mass and the momentum. But in the light that we observed from the classical electromagnetism, it doesn't really need a mass here. Okay, so therefore, there's a very good reason for physicists to think photon doesn't have any mass. But after all, it's really a measurement question. So then how do we actually measure the photon mass? Right? So to measure photon mass, people are actually very clever. They use object very far away from the Earth. So you can have objects that emit fast radio bursts. Those are electromagnetic radiation. And then they can be emitted at different wavelengths. Okay? So then you'll see if an event happens, and then you'll just we can measure detector, then we'll start to register the count. You can measure the arrival time of the radio frequency at a different energy. Okay? So the fact that we didn't really see any difference in the arrival time means the mass, there's no mass for the photon. So they all travel at the speed of light. Okay? If you have mass, then that will cause some heavier particle to slow down. So the fact that we didn't really see any light shift, that actually put a bound on the photon mass to be less than a number that's really small, 5 times 10 to the minus 51 kilogram. All right. So nowadays, we know in physics, this is our fundamental building block. Okay? There are quarks, there are light particles we call leptons, there are also photons, and there are a bunch of other kind of boson, those are related to nuclear decay. There's also something called the Higgs boson. You've probably heard of that. Right? So as physicists, it's our job to figure out how to use those building blocks to make a world, okay, to resemble the world we are living in. But the basic theory, the simplest theory starts with all the particles to be treated equally. Everybody has no mass. Okay? So then the consequence is that now everything will be moving at the speed of light. Okay? And if that's the case, then there's no way for the particles to form bound state. Okay? And then you cannot really form atoms, you cannot form molecules, and then there's no hope in forming the Earth or solar system. So in order to make the world as stable as we have to nowadays, we need to have a way to slow down those particles from traveling, preventing them from traveling at the speed of light. So that's where the Higgs field comes in. So the Higgs field is a field permeating throughout space. And what happens is that this Higgs field can cause the electrons, they interact with the electrons, and it causes the electron to scatter around, therefore slow down the electron. So it can also cause other heavier particles like W and Z boson, which we know are very, very, very heavy. Actually, so they slow down even further. So they hardly travel very far. But as opposed to, say, photon here, the photon doesn't really couple to the Higgs field, so it just travels unimpeded. So therefore, photon doesn't have any mass, versus the other particles can acquire mass. So just like what is this Higgs field? Since we are at Illinois, so I like to use the imagery of the Illinois field, our cornfield, right? So the particles are moving along. Maybe the Higgs field might be, it's more exotic, so it's artist's rendition of the Higgs field. Those are vacuum field the particle has to travel through. And then by interacting with this vacuum field, that causes the particle to slow down, therefore acquire mass. Okay? Now the question is, we have so many different particles. Okay, how come that they are all different mass? Okay, so you have electrons here, pretty light. Different quarks are also pretty light. Top quarks are very heavy. It's very heavy. WZ and other particles are actually heavier. So there's some kind of a hierarchy here in mass. Now the neutrinos are even lighter. So we don't really know why those mass are so different. We can only say, oh, because they bump into this Higgs field at a different strengths. Okay? So that's one way to view this. But now for physicists, we want to come up with a theory that's beyond what we already have to be able to explain the ordering of those mass. So that's still ongoing research, and we don't have answer to that yet. So I want to close this presentation with this imagery. So this is actually weighing the heart ceremony in ancient Egypt. So once a person's dead, right, it will be mummified and then put the heart into this jar so that the heart can be weighed against this feather of truth. Okay? And then if the heart was found to be heavier than the feather, then it was fed to Emmet. So this is a devourer, this is the beast with the alligator hat. And the soul will be cast into darkness. If the scales were balanced, then the deceased can be passed, pass the test, and then taken to Osiris, who will welcome them into the afterlife. Okay? So therefore, in ancient Egypt, they pay a lot of attention in weighing, right? Okay, so therefore, that's why physics is not just for the pursuit of knowledge. There are also a lot of different practical reasons to measure mass very, very precisely, and also trying to understand what's the origin of the mass. So I want to end my presentation, and then if you have questions, please.